Let's begin our second video on Special Theory of Relativity with a discussion on the classical relativity principle. Recall, the principle effectively states, I quote, no mechanical experiment carried out entirely in one inertial frame can tell the observer within that frame what the motion of that frame is with respect to any other inertial frame, unquote. Furthermore, there is no way at all of determining the absolute velocity of an inertial frame from any mechanical experiment that may be carried out within the frame. In fact, no inertial frame is preferred over any other as far as the laws of mechanics are concerned, since they are the same for all inertial observers. Hence, there is no physically definable absolute rest frame at all. This is what we mean when we say all inertial frames are equivalent as far as mechanics is concerned. It also means that there is no single frame that has an absolute or privileged status relative to the other. It's interesting to note here how Newton stated the following principle. I quote, the motion of bodies included in a given space are the same amongst themselves, whether that space is at rest or moves uniformly forward in a straight line, unquote. Now let's consider the situation from an electrodynamic point of view. In other words, suppose we ask whether the laws of physics other than those of mechanics, for instance, laws of electromagnetism, are also invariant or are they preserved under Galilean transformation? If they are, then the Newtonian relativity principle would hold not only for mechanics but for all of physics. In other words, no inertial frame would be preferred over any other and no type of experiment in physics, whether mechanical, optical, electrical or whatever, carried out in a single inertial frame would enable us to determine the velocity of that frame relative to any other frame. In that case, there would be no preferred or absolute reference frame at all. To see this, let's consider the electromagnetic situation and how it is different from the mechanical one as far as Galilean transformation are concerned. Now let's consider a pulse of light, an electromagnetic pulse if you like, traveling say towards a positive x direction with respect to the medium through which it is propagated at a speed c. This medium of light was initially in the early part of the 18th century given the name luminiferous ether, historically because at that time the mechanical view of wave nature of light prevailed. It was not really accepted that an electromagnetic disturbance could be propagated in empty space. Okay, so for simplicity, let us regard this ether frame as the frame S, which is assumed to be an inertial one, in which the observer measures the speed of light to be exactly 2.997 into 10 to the power of 8 meter per second, or let us simply say c, which is 3 into 10 to the power of 8 meter per second. Now, if there is a frame S dash moving at a constant speed v with respect to this frame S fixed in the ether frame, an observer would measure a different speed for the light pulse. According to Galilean transformation, this value of the speed of the light pulse can range from c minus v to c plus v, depending on the direction of motion of the frame S dash with respect to S. Hence, the speed of light is certainly not an invariant under Galilean transformation. So if these Galilean transformation really apply to optical or electrical phenomena, then it is obvious that there is only one inertial frame, one unique frame in which the measured speed of light is exactly c, and that unique inertial frame would be obviously the so-called ether frame, which is at rest. We would then have a physical way of identifying an absolute frame or rest frame just by determining the speed of light or any other optical experiment carried out in some other frame and determining the relative velocity of that frame with respect to the absolute one. This is what Michelson and Morley tried to do. So what followed from the discussion on the previous slide was that the speed of light cannot be the same for observers in different inertial frames according to Galilean transformation. This means electromagnetic effects will probably not be the same for different inertial observers. As a matter of fact, one can easily show that Maxwell's equations are not preserved or they are not covariant under Galilean transformation, although Newton's laws are. So in fact, in going from frame S to frame S dash, one can show that the wave equation changes its form. Now, if we accept that both the Galilean transformation equations and Maxwell's equations are basically correct, then it obviously follows that there exists a unique privileged frame of reference, and this should be the ether frame, in which the Maxwell's equations are valid and in which the light is propagated at a speed equal to c. Now this means we have three possibilities. In this slide, as we see, the first possibility is the following. A relativity principle exists for mechanics but not for electrodynamics. In electrodynamics, there is a preferred inertial frame, that is the ether frame. Now, if this is the correct alternative, then Galilean transformation equation should apply and we would be able to locate this, we should be able to locate this ether frame experimentally from an optical experiment. The second possibility, the relativity principle exists both for mechanics as well as for electrodynamics. But then the laws of electrodynamics as given by Maxwell are not correct. That is why they are not covariant under Galilean transformation. Now, if this alternative is correct, then we ought to be able to perform experiment that will show us that there are deviations from Maxwell's electrodynamic equations prediction. That means there should be some experiments which give us results which are different from what Maxwell's equations predict. Of course, Galilean transformation would again apply in this case. There is a third possibility. The relativity principle exists for both mechanics as well as for electrodynamics, but the laws of mechanics as given by Newton may be incorrect. Now, if this alternative is the correct one, then we should be able to perform experiments which will show us deviations from Newtonian mechanics and reformulate the mechanical laws. In that event, the correct transformation equations would not be the Galilean transformation, obviously because they are inconsistent with Maxwell's equation, but there must be some other more general transformation equations which are consistent with both classical electromagnetism and mechanics, the new mechanics, if I may say. Now, we have already seen that Newtonian mechanics breaks down at high speeds. So you will appreciate when I say, or rather you will not be surprised when I say that probably among the three alternatives, the third alternative is the one which is most probable. And in fact, it is this alternative that leads to Einstein's relativity. In fact, this is the correct alternative. Now, in the slides that follow, we will look at some experimental experimental results which enable us to reject the first and the second alternative. And then we will see what the relativity principle and the actual transformation law is. As mentioned in the previous slide, if the first choice were to be correct, then that is, if a relativity principle exists for mechanics but not for electrodynamics, then there ought to be a preferred frame for electromagnetism where the speed of light is c. This quest for this preferred frame was exactly what Michelson and Morley attempted and what we will discuss in this video. As far as the second choice is concerned, that is that the relativity principle exists for both mechanics and electromagnetism, but the laws of electrodynamics as given by Maxwell are not correct. This alternative is obviously wrong, because there were several experiments which proved that the laws of electromagnetism as given by Maxwell were absolutely true. So, after the Michelson-Morley experiment rules out the first possibility, and the second possibility is automatically ruled out because of large number of experimental evidence in favor of electromagnetic theory, we are left with no choice but to go to the third alternative, that is, to modify the Galilean transformation equations and to generalize Newton's laws so that these laws would now apply in all speed regimes from 0 to c. We will see that in the following slides. So how do we locate this absolute frame or ether? Well, the obvious experiment would be the one in which we can measure the speed of light in a variety of inertial frames, noting whether the measured speed is different in different systems, and if so, noting specially whether there is evidence for a single unique frame in which the speed of light is c, the value predicted from electromagnetic theory. Michelson in 1881 and again Michelson along with Morley in 1887 carried out such an experiment. Now, before we understand this experiment and the result and its interpretation, we will take a further look at the concept of ether. Now, when we say that the speed of sound in air, say at 0 degrees, is 331.3 meter per second, we have in mind an observer and a corresponding reference frame which is fixed in this air mass through which the sound wave is moving. Now, the speed of sound for observers who are moving with respect to this air is correctly given by the usual Galilean velocity transformation, depending on the speed of this observer. However, when we say that the speed of light in vacuum is 3 into 10 to the power of 8 meter per second, it is not at all clear with which reference system is implied. A reference system fixed in the medium of propagation of light presents difficulty because, in contrast to sound, no such medium seems to exist. However, it seemed inconceivable to the 19th century physicists that light and other electromagnetic waves, in contrast to all other kinds of waves, could be propagated without a medium. So it seemed very logical to postulate a medium called ether through which light propagates, even though it was necessary to assume some very unusual properties for ether, such as extremely low or even zero density, perfectly transparency, and also I would say ether was assumed to fill all space, and it was the medium with respect to which the speed c applies. It therefore directly follows that if an observer moving through ether with a velocity v were to measure the speed of light, it wouldn't be c but would be given by the Galilean transformation. So, if ether exists, the spinning and rotating earth should also be moving through it. An observer on earth would then sense what is called an ether wind, whose velocity is v related to the earth, where v is the speed of earth in its motion through ether around the sun. Now, we all know that v is equal to about 30 km per second, and hence the ratio v by c is the order of 10 to the power of minus 4. Now, optical experiments which were accurate to the first order in v by c were not able to detect the absolute motion of earth through this ether. Later, Fresnel and Lorentz showed how this result could be interpreted in terms of the presence of an ether. Of course, this interpretation had difficulty. The issue was not really resolved with first order experiments. It was agreed that a very unambiguous test of the ether hypothesis would require an experiment that measured second order effect, that is, one in which we measure v by c whole squared. In other words, an effect which is in one part of 10 to the power of minus 8. Now, Albert Michelson, who invented the optical interferometer, whose remarkable sensitivity made such an experiment possible. Michelson first performed this experiment in 1881, And then in 1887 he collaborated with E.W. Morley and carried out a more precise version of the investigation, which was destined to lay the experimental foundation of the special theory of relativity. For his invention of the interferometer and for his many optical experiments, particularly the Michelson-Morley experiment to detect ether, Michelson was awarded the Nobel Prize in Physics in 1907. Incidentally, he is the first American to be so honored. We will now see the details of this. We will now describe the Michelson-Morley experiment. We begin with a description of the apparatus. A collimated beam of monochromatic light from a sodium source with wavelength lambda falls on a half-silvered plate placed at 45 degrees to the beam. The incident beam splits into two parts. The reflected beam travels perpendicular to the incident beam and falls on a mirror M2 kept at B and is reflected from it. The transmitted beam falls on another mirror M1 kept at A and is reflected from it. The transmitted beam is also passed through a compensating plate C so that the optical paths of the two beams are equal. The two reflected beams return to the original half-silvered plate and are seen through the telescope. They will interfere to produce an interference pattern much like that seen in an air wedge. The entire apparatus is kept floating on a trough of mercury so that it can be turned through 360 degrees. Initially, the arm PA is kept parallel to the direction of Earth's motion. Let's understand the theory behind this experiment. Let the velocity of the Earth and therefore the entire apparatus be v. Let the path PA and PB be of lengths L1 and L2 respectively. The relative velocity of light beam travelling along PA will be c minus v, and the relative velocity of the beam travelling along AP, that is the one reflected from mirror M1, will be c plus v according to Galilean transformation. Hence, the total time of travel for the path PAP will be, as shown in the slide, TL1 equal to L1 divided by c minus v plus L1 divided by c plus v. Simplification of the result gives us TL1 equal to 2L1 divided by c into 1 minus v squared by c squared to the power minus 1. If we expand the term 1 minus v squared by c squared to the power minus 1 binomially and retain the first two terms, we obtain TL1 equal to 2L1 divided by c times 1 plus v squared by c. Let's now consider the ray reflected from the mirror at B, that is mirror M2. By the time the light hits the mirror at B, say in a time t, the mirror would have advanced forward by a distance Vt. Hence, we have from the geometry of the figure, by applying Pythagoras theorem, Ct whole squared equal to L2 squared plus Vt whole squared. Solving for t, we obtain t is equal to L2 divided by root of c squared minus v squared. On further simplification, we get t equal to L2 divided by c times root of 1 minus v squared by c squared. If you take root of 1 minus v squared by c squared to the numerator, it becomes 1 minus v squared by c squared to the power of minus half. Expanding that binomially and retaining the first two terms, we obtain finally t equal to L2 by c into 1 plus v squared by 2c squared. Therefore, the time taken for the light to go to the mirror M2 and come back, that is the time taken for the path PBP, would be TL2 equal to 2L2 by c times 1 plus v squared by c squared. So, now the time difference between the paths PAP and PBP will be delta T1 equal to TL1 minus TL2. Substituting the values of TL1 and TL2 and simplifying, we obtain delta T1 equal to 2 by c times within brackets L1 minus L2 plus v squared by c squared within brackets L1 minus L2 by 2. Now this time difference will give rise to a phase difference between the two light waves reflected from the mirrors at A and B, and hence will cause an interference pattern to be observed. Now suppose the whole apparatus is turned through 90 degrees such that the paths L1 and L2 are interchanged, then a similar analysis will give the time difference between the beams as delta T2, which is equal to 2 by C within brackets L1 minus L2 plus V squared by C squared times L1 by 2 minus L2 as shown in the figure. Clearly, there is a difference in the two time differences delta T1 and delta T2. Hence, there will be a change in the phase difference in the two cases, which means there will be a shift in the fringe pattern. This shift in the fringe pattern can be calculated as follows in the next slide. The shift in the fringe pattern S is calculated as follows. The difference between the time differences delta T1 and delta T2 before and after the 90-degree rotation of the apparatus is given by capital delta T equal to delta T1 minus delta T2, which yields V squared by C cubed times L1 plus L2. Now, if the time difference between a pair of interfering waves changes by T, the period of the wave, then the shift in the fringe pattern will be one fringe in the field of view. This is well known from optics. Hence, for a time difference of delta T, the fringe shift will be S is equal to capital delta T divided by T. Substituting for capital delta T, we obtain S is equal to V squared by C cubed times L1 plus L2 divided by T. The term C cubed in the denominator can be written as C squared into C, and if you take the C multiplied by capital T, that is C into T, we obtain S is equal to V squared by C squared times L1 plus L2 divided by C into capital T. Clearly, C into capital T is equal to lambda, the wavelength of light. Hence, the shift in the fringe pattern is given by S is equal to V squared by C squared times L1 plus L2 divided by lambda. Having calculated the expression for fringe shift, let us estimate the value of S. The values used by Michelson and Morley in their experiment was L1 and L2 was 10 meter. The wavelength of light was 5670 angstrom unit or 5.67 into 10 to the power of minus 7 meter. The speed of Earth through ether, that is the orbital speed of the Earth, was V equal to 30 into 10 to the power of 4 meter per second, and the speed of light C was 3 into 10 power 8 meter per second. Substituting these values gives us a fringe shift of 0.4 of a fringe, almost 50% of a fringe. Now this may appear to be very small. However, the instrument had a sensitivity which could detect a fringe shift of 1/100th of a fringe. The experiment was performed very carefully and it was observed that there is no fringe shift whatsoever. The experiment was carried out at day and night and at different times of the year. Every time a null result was obtained. Now this was extremely unexpected result. Now what is the implication of this null result? The obvious implication is that there is no ether medium with respect to which the earth or light is moving. If we substitute V equal to 0, we will not obtain a fringe shift as can be seen from the expressions. The second and probably a more important conclusion is that the speed of light does not depend on the motion of the observer. It is a constant. Now this result where we did not get a fringe shift, the expected fringe shift, is often known as the null result of the Michelson-Morley experiment. This null result of the experiment has far-reaching implication as we will see in the next video. With this, we come to the end of video number 2 in this course on Special Theory of Relativity, where we have elaborately discussed the Michelson-Morley experiment and its consequences. We note that the end result of this experiment is that the speed of light does not depend on the observer who measures it. There are several extremely good books on special theory of relativity. I have chiefly followed the book written by Robert Resnick, published by Wiley Student Edition 2014, An Introduction to Special Relativity. I acknowledge the author for this wonderful book on relativity.